Okay, get started. Hello, everyone. Welcome. Happy New Year, and welcome to the Winter Quarter ECE Colloquium series. So I'm the associate chair, so it's my job to say a few things about the colloquium for the students. Register this colloquium as a class, right? We ask you to attend this colloquium as frequent as possible in person. Another assignment to get the credit is to turn in a take-home message on Canvas immediately after the talk, right? So we know you were here. So we open a 1-hour window. So this year we scheduled 5 talks. It's much less than usual because the faculty recruiting season. So we expect faculty candidates to give you talks. So to receive the full credit, we ask you submit at least 4 out of 5. Okay, so it's a little bit increased from last year because last year we asked half, then we see you binged in the first half, then later half nobody comes anymore. Less people come anymore. So we increase the standard. Okay, so it is my pleasure to introduce today's speaker. She's one of us, Professor Sara Mouradian. She's gonna tell us her exciting research and plan for building a scalable quantum computing system on campus. So Sara received her bachelor's and the PhD both from MIT. She then did an intelligence community postdoc fellowship at UC Berkeley, where she worked to building useful quantum sensors based on trapped ion system. So here her research focused on building really robust and scalable quantum system for the next generation quantum computing, quantum communication, and quantum sensing. Without further ado, Sara.
Perfect. Thanks so much, Mo, and welcome to the quarter, everybody. So today I'm going to talk about how we as electrical engineers can help build quantum technologies at the scale where they start to become useful for real-life problems and not just for publishing Nature and Science papers, although, of course, we hope to do that along the way. So let's start with the basics. What is quantum mechanics? Quantum mechanics is the science, the description of what happens on the atomic scale. So everything around us, of course, is built out of atoms, but we see their collective processes, their collective interactions, and that's what we call the classical world. But if we wanted to know what happens when a hydrogen atom meets a carbon atom to create a hydrocarbon, we need to understand quantum mechanics. And one of the main important parts about quantum mechanics is that the states are quantized, hence quantum mechanics. And what that means is if you have some atom, here helium, you have some electron, some nucleus, and in general, the electrons are found in the ground state, so the lowest energy configuration. But if we hit the atom with some energy, the electrons can be excited to higher energy states. But the important thing here is that there's only discrete quantized levels that those electrons can inhabit. So that means if I look, it goes into this excited state, and if we wait some time, the system will decay. And as the electron falls back down to the ground state, it will emit the energy, because we have to conserve energy, of course. And that emitted energy will take the shape of a photon, or a particle of light. And that light will have the frequency, and thus the color, of this transition. So if we look at all the light that a certain atom can emit, you'll only see discrete bands. So for instance, in hydrogen, you'd see these 7. For helium, you'd see more, et cetera, et cetera. But you have these discrete quantized states. And that will become important later on when we want to use these systems. So at some point, scientists thought, OK, we have all of these states, but what if we ignore all the top ones and we only take the ground state and the first excited state? We have a 2-level system. And a 2-level system, what's a 2-level system that we know at best, is a classical bit, right? A classical bit that can be 0 or 1, on or off. So now what if we think of, and we know that classical bits can encode some information. And 1 bit encodes 1 bit of information. And so they asked themselves, what would 1 bit of quantum information hold? Right? And so if this is a bit, we're going to call this a qubit, or a quantum bit. How are qubits different? So classical bits, of course, can be 0 or 1, whereas quantum bits are described not by just a single number, but by a vector. So this vector has A in the 0 direction and B in the 1 direction. We just put these brackets around it to feel good about ourselves, feel like we're being fancy, but also to denote that we're talking about something quantum. And so this describes some vector along the unit sphere. And so these coefficients, A and B, can be complex. So they can be real, they can be imaginary, they're complex numbers. And so it could be 0, we could have 1, we could have a superposition state, so that when you have a little bit of 0 and a little bit of 1. But one important thing is because we're talking about the unit sphere here, the block sphere, the amplitude squared of these coefficients must equal 1. Okay. And then things start getting a little bit complicated, or more complicated, when we talk about measurement. If we measure a classical bit, we measure exactly what we set. So if I give you 100 0 bits, and then you measure those, and then you send them to your friend, and they measure all 100, they'll always measure 0, right? Or if I give you a 1 bit, you'll always measure 1. In a quantum bit, things are slightly more complicated. So if I prepare this state here, if I prepare thousands of this state here, and I give them to 1,000 friends, the probability that they will measure 0 will be A squared, and the probability that each of them will measure 1 will be B squared, right? So at every measurement I make, it will be either 0 or 1, but it will follow some probability distribution with these, given by these probabilities, given by the squared of the amplitudes of the state. Okay. And to drive home this point, so here I come back to my unit sphere. This is the 0 state, this is the 1 state. This arrow represents the state that I have created. It's pointing to the 1, so I've created a 1 state. If I create this state thousands of times and then I measure each one of those, the probability that I measure 0 is 0, and the probability that I measure 1 is 1. However, if I prepare a state somewhere along the equator, and then I measure that, I'll measure 0 with a probability of 1/2, and I'll measure 1 with a probability of 1/2. And this also brings up another very important point, which is that because the probabilities of measurement are the amplitude squared, we actually erase any phase information that we might have. So we can't make any measurement that, if we measure in this basis, we can't make any measurement that tells us what is the phase of this vector. Right? This could be 1/2 0, 1 over root 2 0 plus 1 over root 2 1, or 1 over root 2 0 minus 1 over root 2 1. But either way, we'll get the same probability distribution for our measurements. This will also become important later. So it kind of seems like, okay, we can encode lots of information somehow because we have this full block sphere instead of just 2 states. But when we do the measurements, we always collapse to one of 2 states. And then the last thing that I won't really talk about in detail because we could spend a whole course on it is entanglement. So 2 classical systems can be correlated. The state of one variable could be correlated with the state of the other. For instance, if it's raining in Tacoma, it's probably raining in Seattle. Those 2 things are correlated. But quantum systems can have stronger than classical correlations, and this is what we call entanglement. So if I have 2 quantum systems, A and B, this is a joint entangled quantum state, and so if I measure 0 for A, I know that I'm in this part of the state, and so I'm going to measure 1 for B. And that's a definitive statement, and it is something that is stronger than classical. Okay. So that's quantum bits, and then if we have lots of quantum bits, we can say we have some quantum information. Those quantum bits encode some quantum information. So how is quantum information different than classical information? And I've borrowed this analogy from John Preskill, who is a leader in quantum information, and he gave a really nice talk if you want to look at it and learn more things. So classical information, if you had a classical book, we get information by reading page after page. Every word, every chapter, every sentence gives us a little bit more information. In In contrast, a quantum book, you have have all these states that have some superposition. They're all entangled with each other. So all our quantum bits, all the information is entangled with each other. And if we read just the information encoded in one quantum bit, we don't get more information. We don't get one bit of information about our entire state. Instead, oh no. Okay. Instead, information is saved in the correlation between pages. And so we don't get any information from reading individual pages. So in the end, we're going to have to be doing joint measurements over many parts of our quantum state to get something interesting out of it. OK. So let's say we want to write this quantum book, have a lot of quantum information. So we want to engineer some quantum system to be useful. What can these engineered quantum systems do? Well, the first thing, simulation, is kind of the first thing that was ever thought of. Feynman thought about this in the, 70s, 80s. He was thinking, as I started this talk, the world around us is quantum. So atoms are quantum. It's really hard to simulate quantum systems on classical computers because the degrees of freedom are so high and because they encode different physics. So it seems plausible that if you engineered a quantum system to look like a quantum system that you cared about but couldn't engineer, then maybe you could get some information about your system of interest. And so an example of that could be simulating nitrogenase. And nitrogenase is a molecule that's used in production of fertilizer. So to get energy from fertilizer and make plants out of it. I'm not a chemist. But apparently, it's hard to make this particularly efficiently. And maybe if we knew how this worked, we could tweak it or make an artificial process that could improve our fertilization output and save world hunger. But it's near impossible. It would take way too long to simulate this on a classical computer. And the hope is that maybe with a quantum computer, we could engineer a quantum system that encodes a lot of the dynamics that are inherent, or at least the important dynamics that are inherent in this molecule, and then use that to understand more about it. Okay. But we can also do more computation-y things. It turns out, and so this was in the 90s by Peter Shor, that you can use a quantum computer, quantum information, to factor a number into its prime factors asymptotically faster than you could with a classical computer. Okay? So and this is important because most of the encryption some of the encryption that we use today is based on this RSA encryption, which it relies on the fact that it's really, really difficult. If I give you a really long number, it's really difficult to factor it into its prime factors. And it turns out that actually the same algorithm, similar algorithm, quantum algorithms can be used to break other types of encryption that are also used. Okay. We can also use quantum systems for atomic clocks, and actually this is one success story of quantum physics already. The GPS that you use on your phone to tell you where you are in the city is actually based out of atomic clocks that are around. And they're able to give you precision on the order of tens of meter scale. And that works. I said that you have these discrete energy levels. And if you measure that very precisely, those energy levels always have exactly the same frequency. And you can turn frequency into time. So if you can measure that frequency very exactly, and you know that it's stable, because atomic systems are always stable, they're all exactly the same, then you can measure time really well. So a lot of work is being put into making these systems better and better. There have been proof of principle demonstrations that have been able to keep time down to 1 part in 10 to the 19th. So that's incredibly, incredibly accurate. OK. And then the last thing is that quantum systems can be used to create provably secure communication. And that's helpful since we're also breaking provably secure communication. OK. And so we started off here with quantum theory that was developed in the 1920s. By the 1960s, we understood enough about quantum information to build what I would call the first wave of quantum technologies. And in these quantum technologies, we need to understand what quantum mechanics to be able to build these technologies. So these are things like MRI, where we're measuring the spins of hydrogens, or lasers, where we're using these, these quantized levels to create stimulated emission. But we're not actually controlling the quantum system, right? We need to understand it to be able to use it. So you can think of it maybe as wind turbines, right? We're not controlling the wind, but we're using the wind to create some energy, right? But so, yeah, that's kind of where they were in the 60s. And then in the 90s, two things happened somewhat simultaneously and also separate from each other, which was kind of interesting. One is that quantum computing theory started to come into play, so that the prime factorization algorithm that I told you about earlier, that was developed in the early 90s. And at the same time, people in NIST were starting to be able to control single atoms, and actually single ions. And so I'm going to be talking about trapped ions today. And these were the pioneers of the field of quantum information, experimental quantum information processing, and also the exact field that we'll be talking about today. Can't really see it, but this is Dave Wineland and Dave Itano. Not sure who those two are. But they won the Nobel Prize for it, and Dave Wineland's now nearby in Oregon. So these two, we got some use for quantum systems, and also started to be able to understand and control these quantum systems. And then it took the next 30 years, people have been working to improve the control, working to increase the size of the quantum systems we can control, until in the last year we've created large enough systems to show quantum advantage. And so, okay, now I'm a pedantic experimentalist, and I would say that this quantum advantage for, I would say, everybody in the room is not particularly interesting. It's like, let's take the hardest possible problem for a classical computer, something a classical computer is incredibly bad at, but it's a problem that's also incredibly easy for a quantum computer, and see who does it better. And the quantum computer, by some measures, but not all measures, did it slightly better than the classical computer. So I would say for a real world scenario, we're not quite at like an advantage that we would care about, but it's important for theorists to start to understand where some of our assumptions start to break down. But our end goal always is to build a large engineered quantum system that can actually do something that's useful for the real world. And that has not yet been done, and that is the goal of many people, including our lab. So, right. So what we want to do is build a fully fault-tolerant universal quantum computer. What do I mean by that? So fault-tolerant means that we don't have to worry about errors. So when we have a classical computer, we don't worry that the transistors are doing something wrong. If our computer program messes up, we know it's probably our fault and not the computer's fault. We want the same thing to be true about quantum computers. Right now, it's probably the quantum computer's fault. We also want it to be universal, which is somewhat technical, but it just means that we can, in principle, do anything with infinite time in qubits in the same way that our classical computers, in principle, can do anything with infinite time. And this just means that it's going to be, if it's universal, it'll probably be useful for the things that we want it to be useful for. So why is this so hard? We can see if we look at the bit errors, right? So classical bits have errors approximately 1 every 10 to the 17th times. Okay, and this actually is starting to be due mostly to quantum mechanics, actually little electrons tunneling between the very, very, very small transistors. But this we in general don't have to worry about. But if we look at today's state-of-the-art quantum bits, and so this is not like your average quantum bit. This is like the state-of-the-art stuff that gets published in very high journals. We have operations 1 every 1,000. We have errors 1 every 1,000 operations. Maybe some can get to 10,000 operations, but still we're 14 orders of magnitude worse in the quantum world than the classical world. So this is a huge threshold to overcome, but that's what we're working on. So I would say that this looks a little daunting and a little scary. How could we ever make quantum information processor that looked like a classical computer with so many errors. Luckily, we can use error correction. If any of you were here last quarter, you might remember a talk from Matt Hastings from Microsoft, who talked a lot about error correction. I will talk only a little bit about error correction. Just this slide. So in error correction in general, the idea is to encode your data into some larger space so that any little bit of error will have less of an effect. It's a very hand-wavy, broad definition. And so you get reduced logical errors, but the trade-off that you get is that you need more physical qubits. So right, if I only had one qubit, if I have an error on that one qubit, the information is totally lost. If I encode my state in 16 qubits and I have one error, I still have, most of my information is correct. The technical, there's a whole field of quantum error correction. A very simple example is that if I had that state that I showed in the beginning, instead of just having this single qubit that's in a superposition of 0 and 1, I could have 3 qubits that encode the same state, and this will protect me against one type of error. We can, it turns out luckily that you can prove that for some certain codes, if you're able to get your errors below some threshold, you can, in principle, build a logical qubit with fault tolerance or with errors much, much lower than you'd ever need. So the surface code is one of the leading types of error correcting codes. And these numbers depend strongly on the exact error model and the exact code and many things. But to give you an idea, if I had physical qubits with error probabilities of less than 1 in 1,000, and I had 10,000 of those physical qubits, I could make one logical qubit with error probabilities less than 10 to the minus 15th. Okay, so this all sounds good. That means we can create logical qubits with very low error probabilities. But then that means we need 10,000 physical qubits per logical qubits. So if we look at then what we need for a problem that would be relevant, for instance, simulating nitrogenase, the requirements are you need 10 to the 8th physical qubits to be able to do this, and 10 to the 14th operations. And today's systems have about 100 qubits, and about 100 gates. So we're orders of magnitude off. And again, these numbers are, depend on a lot of different things, but the orders of magnitude are more or less there. Okay. So this is what we're trying for. And so that was kind of the beginning of the end of the beginning of the talk. If anyone has questions about the basics before we go to the specific implementation, now would be the time. Yeah?
So as far as something like the nitrogenase simulation goes, is the goal more to reduce the number of processes and gates needed, or is it to raise our dependable gates processes to that level?
Great question. People are working on both sides of that problem. So I'm working on bringing up our hardware, and then there's lots of theorists working on bringing down the requirements. Yeah. I saw another question, maybe. Yeah.
The nitrogenase problem is like ground state.
Yeah.
So that seems super hard. Aren't there easier things? Because it seems like you're very close to the threshold.
Yeah. Yeah, so there are easier things. I picked that one because it's particularly relevant. But I think, yeah.
There's not even an algorithm that says the ground state can't do 100%.
Sorry?
So ground states of Hamiltonians is hard on quantum computers too. So in general, you won't expect to be able to solve it even with the quantum computers.
Yeah, that's true. I do not know, to be frank, the exact details of those numbers and how they were encoding the algorithm, but it's found in this paper. Yeah.
So the main issue with doing fault tolerance is like the overhead that you have.
Right. Yeah. The main takeaway here is that to be able to do something reasonable with nitrogenase, you need fault tolerance. And if we look at today's error rates and today's error correcting codes, these are the orders of magnitude that you need. that's the takeaway, I would say, from the slide. Yeah.
So the main way we are getting rid of faults is just to do a whole bunch of the same operations in parallel on different bits, right? And then compare the outcomes and kind of see what's most likely.
So maybe I'll just stop you. It's not exactly that simple. You have to, it's not quite that simple. We set up these large error correcting codes, and you do some sequence of operations on there to encode your problem, and then finally to read out your problem. It's not a parallel situation. But good question. That's one of the biggest misconceptions about quantum computing. You're not just trying lots of things in parallel. Cool. All right, so if there are no more questions, we can go on to my favorite qubit, which is calcium ions. So we use calcium-40 to be exact. That's the isotope of calcium that we use. We rip off one of the electrons to make it a positively charged ion, so we use calcium-40 plus. And we use two electronic states like I talked about before, some ground state of the electron and some excited state. These are not the actual wave functions. The actual wave functions are much more complicated. But this is just to remind you of chemistry that you may have taken earlier in your career. And we use a laser to drive to create a state, to drive transitions between the 0 state and the 1 state, to create any superposition that we would like. For the experts in the room, this is a quadrupole transition, so this is a very long-lived excited state. Okay, and one thing that I'd like to stress here, and I'd like to turn you all into proselytizers for trapped ion qubits, is that all ions, what makes trapped ions great is that all ions are exactly the same. This is like a fundamental thing of physics, that every ion is like the instantiation of like a single calcium-40 field, right? And more or less. And so in some sense, building a quantum computer from ions is a classical problem, right? We need to get our our qubits are great. There's nothing wrong with our calcium ions. The thing that's a problem is our classical control infrastructure. And we'll talk about that, what the problems are as we go on. And this is maybe in contrast to something like superconducting qubits, where you fabricate your qubits and the quantum properties are due to your fabrication. And so maybe if you were having a bad day in the clean room, or it was slightly more humid in the clean room, your qubits will have slightly different properties. But that's not true in calcium or in trapped ions or atoms, because all ions are exactly the same. So we control our qubit all with lasers. This is the transition that we use. This will be the only jargony slide perhaps, but we use one of the 2 states in the ground state, S1 half manifold, and one of the 6 states in the D5 half manifold. This is a quadrupole transition, as I said before, and we use 3, and this is 729 nanometers. You can barely see it, but it's the red. And we use 3 other lasers, one in the blue at 397 nanometers, and 2 in the near infrared around 860 nanometers. And these are used to prepare the state and also read out the state. And so if we prepare our qubit in the 0 state, then we wait some time later and we measure our qubit a second later, it's still going to be in the 0 state. And this basically is always there because, again, it's a ground state. It's the energetically most favorable state for our atom to be in. So it will always remain in this ground state. If I prepare my ion in the 1 state, and I wait some time, there will be a very, very slow decay just due to the natural transition between the 1 state to the 0 state. And this 1 state has a 1 second lifetime, so the 1 over e time is about 1 second. 1 over e squared. But that's long enough, let's say. The real problem comes when you want to create a superposition state. So when I want to create this 1 over root 2, 0 plus 1 over root 2, 1, you can see that it decays much, much, much more quickly. And while this is limited by physics, and there's not much that we can do about it, this is in fact limited by our classical control fields. So it's limited by magnetic field noise. It's limited by our laser noise, so laser frequency noise, laser amplitude noise, and laser phase noise. And so, so this is 200 milliseconds. I would say that that is kind of This was a very well-engineered system. Most systems have coherence times around 10 milliseconds. And so to reach this 200 milliseconds and then push it up even higher to its fundamental limit, you need stable magnetic fields. So you need to know E&M simulation. This is something you'd learn in EE 361. And we also need stable laser amplitude. So we need to be able to measure the amplitude of the laser, measure the frequency of the laser, measure the phase of the laser, and feedback on the laser itself to create a very, very stable system. And so that's something that you would learn in control systems, like EE 447, for instance. It's just to emphasize that these two problems in particular, and actually all the problems that we'll see, are fundamentally electrical engineering problems. Okay, so that's how long our qubit remains coherent. How do we do operations? We do operations, as I said before, by having this laser, 729 nanometer laser, on for some particular amount of time. That excites the system from the ground state to the excited state and back and forth and back and forth. These are called Rabi oscillations. And we can stop at any intermediate point to create whatever state that we would like. And we can do one operation, so turn the qubit from the 0 state to the 1 state in about a microsecond. That's limited by our laser power. And so let's imagine that I've blown up this graph. Remember, this is in seconds, and this is in microseconds. And this red line is the same red line that's pointed here. And you can see that we have no decoherence at all. And this is not data. This is simulation. But we have no decoherence at all in the first 10 microseconds. And that's where that 1 in 1,000 number comes from, right? We can do even more, really, single qubit operations by the time this by the time our decoherence starts to take effect. So if we look at the specifications of our trapped ion qubit, we have a T2 time of 200 milliseconds. That's what we said before. That's the decay of our superposition state. Our 1 qubit gates can be done in 1 microsecond with 4 nines of fidelity, so error less than 1 over 10 to the 4th times. 2 qubit gates, again, I won't really talk about how we do that entanglement, but suffice it to say, in trapped ions, it's actually quite easy, and I'm happy to answer questions about it at the end of the talk. But we can do, or the record currently is 30 microseconds with 3 nines of fidelity. 2 qubit gates are almost always the hardest gate in any system. And preparing the state that we'd like, or in our ground state, and also measuring our state, we can do that in state-of-the-art 50 microseconds with 4 nines of fidelity. These are not just hero experiments. So in our lab, each one of these would be like a big paper, or at least these 3. But in our lab, which is not looking to be the world leader in qubit fidelity, but rather the world leader in scalable systems, this is what we are hoping to get. So we're hoping to get about 10 milliseconds of coherence, just because there's always trade-offs. But yeah, 10 milliseconds of coherence. We can probably hit this single qubit gate fidelity. The hardest part about this is actually measuring really high fidelities, because if you're only having errors 1 in every 10,000 times, you need to do a lot of measurements before you have enough statistics to reliably say that that's your fidelity. Our 2 qubit gates, we'd like to go a little bit slow, 100 microseconds, 98% fidelity. And state preparation and measurement, we can probably get about there. And again, the hardest part is always doing the measurements. And if we look back to what we need to build a logical qubit, we're there, basically, right? Or at least the state of the art is there. We have physical qubit error probabilities of less than 1 in 1,000. And so now, all we need to do is trap control and measure 10,000 ions to create 1 logical qubit, and then also scale that up by orders of magnitude to do something useful. So how do we trap ions? We start with calcium vapor. So we start with calcium. Well, let's say. We start with an ultra-high vacuum system. So a system that has it's at 10 to the minus 11 torr. That's a better vacuum than the deepest depths of space. So you'll be more likely to run into a hydrogen atom in the middle of the deepest depths of space than you would in our vacuum chamber. Inside of that, we put all our trapping electronics as well as a big chunk of calcium. We heat that calcium up to above the vapor pressure, and that creates calcium vapor. We then use 2 lasers, all about lasers in this field. We use 2 lasers to ionize our calcium, and that gives us a calcium vapor with lots of different isotopes and allows us to just get calcium-40 ions. So the first laser excites it, this is isotope selective, excites it to an excited state, and the second laser kicks the electron out of the atom altogether. If we do that within a trapping region, we can then trap it. So the nice thing about ions is that they're ionized, so they have a charge, which means they interact with electric fields, which means that we can trap them in electric fields. And if you take an EE361, perhaps you remember that you can't create a totally trapping field. So you can't create an electric field that a particle would be trapped in all 3 directions. It always has to escape in one direction. But we play a trick, and we use RF fields. So this is so this is going to be a simulation. Think of it as gravity, but you can also think of it as electric field potential, right? So this is electric field potential. This is a freeze frame. You can see this ball, signifying our ion, would just escape down here, right? This would be like the lowest energy. It would escape out down here. But if let's see if this works. Yeah, so now we have this RF field. So the RF field is the positive and minus are switching back and forth. And so the ion can't ever escape. And as long as that RF frequency is much higher than the frequency of the ion's movement, then we can keep that ion trapped. So that's what we do in 2 dimensions. That's what these RF electrodes are for. So we put 2 RF signals, well, 1 RF signal split over these 2 pairs of electrodes. That creates a RF confining potential in 2 dimensions. And then we just use DC electrodes in the other dimension, and that allows us to create a confining potential in the 3rd dimension. And with this, if we get the potentials correctly, we can trap a string of ions. Right? And the number of ions that we can trap here is not like totally limited. People have done up to 50. Actually, people have done up to like 250. That's not really the limiting factor in this technology. I'd also just like to mention that you can feel proud because one of the people who won the Nobel Prize for trapping in this way then later came to UW. This is DeMelt. And so if you go to the physics building and you look, you can actually see a quadrupole trap etched into the side of the building in his honor. Okay, so this is a schematic of a super, super simple trap, but now people do very complicated electrode patterning. So this is, all of these little bits are electrodes. These are DC electrodes, and the RF electrode is this big one here. And this trap was made at Sandia National Labs. It's called the high optical axis trap. And it allows you, with all these little DC electrodes, we can A, trap lots of ions, but also B, shuttle them around. So we could shuttle an ion over here. We can move some over here, some over there. So now this is starting to look like a scalable quantum processor where you could have some ions here, and some ions there. Right? And you could even think about tiling this more and more and trapping as many ions as you think you might need. But of course, to do this, we need to be able to do simulations of these electrodes to make sure that you can see these electrodes have strange shapes, and that's to make sure the potentials are exactly as we want them to be. So to iterate on this and make it even, so this is good, but it's not optimized, it's not optimal, it's not the best that it could be. To create better structures, we need efficient RF delivery and also very harmonic potentials. And again, this, taking EE361 gives you most of what you need to be able to do these simulations. We also need to be able to pattern these electrodes. So we need very precise patterning, and there, UW is also has a great fabrication facility, which you can take in my fabrication classes, and also as an undergrad, you can become a staff person there. So you can learn things and make money at the same time. Okay, so that's how we trap ions. Then how do we control tens or eventually millions of ions? So we have this nice little chain of ions that trapped in our harmonic potential. The spacing between ions is about 2 microns. And more or less on each ion, we need to focus all of the 4 lasers that we need to control the state of the ion. Okay, there's some, you can do a little bit better than this. There are some tricks you can play to not need 4 lasers on every ion. But in general, this is the kind of order of magnitude that we're talking about. And then if we want to do high quality control, we need 4 orders of magnitude on-off isolation and also ion-ion isolation. So if I'm shooting a laser on this ion, we want to make sure that none of it's leaking onto its neighboring ions. Right? And that 4 orders of magnitude comes from if we want errors 1 over 10 to the 4th times, then we need this 4 orders of magnitude, hand wavy. We also need megahertz switching speeds, right? The gate operations are in a microsecond, so we need to be able to turn our lasers on and off at that time scale. And we need tens, okay, eventually millions of individually controllable channels. And right now, we need flexible beam reconfiguration because we're still doing experiments. We don't know exactly where we want our ions to be, but maybe in the future, once we build a really great trapped ion quantum computer, we don't actually need reconfiguration. So how do we control one ion? So these are pictures from the lab I did my postdoc in. Of course, the lab that's starting here at UW will be much cleaner than this and will not have cables anywhere. But this is what we call the laser room. This houses all the lasers for our ions. And this probably can control approximately 10 ions, right? If we had more, we need more laser power. We need more optics. And you can see it's quite a mess. And then these here, so this is just the laser sources. Then we need to modulate the laser sources on and off. These are the optics that we need for actually half of one ion. So we need double this, and each of these the spacing between these holes is 1 inch. So this is like a few feet, or maybe 3 feet or something. So that's a lot of space per ion per channel. That clearly needs to change if we want to build a quantum computer. So instead, we'd like to go to integrated photonics. So now I've added this little picture to scale on this picture of the free space optics. And you can see that if this is one channel, actually half of one channel, this little thing down here can have 256 channels. And this is integrated photonics, so photonics that are integrated onto a chip. It's kind of in the same idea of integrated electronics, right? Going from tubes to on-chip transistors. That's kind of what the field of photonics is doing right now, especially in the visible. So free space optics are great. They're easy. You can get a really high quality beam shape, but they're bulky, right? You need about 1 meter for a full active pass. And they're also large power, so I didn't really talk about it, but switching these beams on and off, you use RF signals, and you need about 1 watt per channel, right? And that is huge. So now if we wanted 1 million watts, a megawatt, that would be prohibitive. Also, they're hard to align and not flexible, especially when you're talking about aligning them onto the ion. You can ask a grad student to align one laser to 1 ion. Maybe you could ask them to do it to 2, but if you want to do 10, they probably ask you not to ask them that. On the other hand, integrated photonics, they're compact. They can be quite fast. They're stable also because they're compact, so we can temperature stabilize them. We can mechanically stabilize them much better than we can this very, very large system. You need significantly less power to modulate each channel, and this is something that people are working on here and elsewhere. But of course, this adds complexity, and these systems really are at the cutting edge of what is possible today, right? So, especially for visible light, which is what we need, especially for UV, which is really which is also necessary. These systems they're definitely not plug and play. There's still a lot of work to be done to make them up to the same quality as what you can get out of a free space system. So what we're building in our lab is a test bed to try to test these systems, right? So we have this UHV chamber, ultra-high vacuum chamber with a trap inside it. The trap and the chamber are both optimized for high fidelity storage and operation. And then on the outside, we put a PIC. This is a similar one to the picture I showed you before, but now you can see all the little wire bonds to the electric pads to actually do the switching. And then in the middle, we'll have some optics it's a spatial light modulator, to rearrange the beams coming out of this integrated photonic circuit and image them onto our ions. Also fix up the beam shape. And this allows for us to keep iterating these new integrated photonic circuits. While simultaneously optimizing trapping geometries and quick testing of these photonic integrated circuits. And what's needed here is efficient visible to UV light modulation, high quality beam shape, and you can take these classes, 487 and 488, to learn about a lot of to learn how to make these systems better. Okay, but that's just one little thing that we're doing in our lab. The full dream of the lab is to, of course, have a system that can support or has a hope to support millions of ions, so qubits at a scale where we can actually do quantum information processing. To do that, we need a significant number of improvements. We need new trapping architectures. We need high quality potentials, efficient RF potentials, and low noise. To do this, we need better ways to simulate and optimize our electric field potentials. Right now, we can do these simulations, but we can think about how we would like to optimize, but there's no, one thing that we'd like to do in our lab is create a full circle of simulation, numerical optimization, and then fabrication and testing, so that we don't have to, we can get a really optimized structure. And second, we'd like to integrate peripherals, so not just having the electrodes on one chip, but having everything integrated seamlessly, right? So if these are the electrodes, this is our little ion. We have the laser control right there, so we don't need a bunch of free space optics imaging our laser output onto our ion. We have detection optics also right there up on the trap, and also nearby some classical logic, because one thing that I haven't talked about is to do the error correction, you actually need to measure your state, process that information that you've gotten, and then feed back on the state of your ions, right? And you need to do all of that well faster than your coherence time. And so if I have to send via USB back to my computer and then see what happened and then send it back, that's never going to work, right? We need fast and dedicated logic. And so hopefully that could all be in one big block. And then, of course, we also want to use these systems. I've talked a lot about the engineering challenges, but there's also, I quipped in the beginning that it's a classical problem. That's not, of course, completely true. There's still a lot of understanding that we need to do about how to manipulate quantum information well at the scale, at a necessary scale. And so some of that is efficient calibration. Think of all of those lasers, all of those electric fields. They could be varying slowly on time. If how do we calibrate all of those fields to get very incredibly high fidelity gate operations and not spend all of our time calibrating instead of all of our time computing? We also, when we're building up these architectures, we should probably think about what we want to do and what error correction we would like to apply, and build these systems not just in Keynote, but also build them with with our final architecture or final use case in mind. And then I've talked a lot about how calcium ions are great, and calcium ions are great. We use 2 particular levels. There's no reason we couldn't use other levels, right? And there's still a lot of questions remaining about what is the best qubit implementation to use. How can we use the full potential of the calcium ion or any ion, any quantum system to get the most out of our quantum processors. And with that, I'd like to thank the team that's working with me, as well as our collaborators, Scott here helping with control electronics, Mo working on integrated photonics, as well as collaborators at other institutions. And with that, I'm happy to take any questions.
So you've been talking about calcium-40 ions, right? So would you say that calcium-40 ions are best for like all potential applications of this technology, or is it possible that different isotopes, even different elements might be better for different applications, or even a mix?
Yeah, great question. I would say that there is no obvious best ion. I like calcium. What's nice about calcium is that the wavelengths, the laser wavelengths are nice, but it's not totally clear that it's the #1 best. That's also because we're far away from fundamental error limits. And actually, probably in the end, it will be some combination. We use different isotopes or different species all in the same trap and use some things for some things, some ions for one thing and some ions for another thing. Yeah.
I have a question. So looking at this picture, the ions are all trapped in columns, right?
Yeah.
So while neutral atom people can trap in two-dimensional lattice,
Yeah.
do you imagine you have to, go across column to column, communicate quantum information, or even entangle them in between?
Yeah. So one thing I would say this picture of it in columns. This is kind of comes to the architecture considerations bullet point. It depends how you're going to encode your logical encoding. Ions, even if they're in a line, can be entangled. Any two can be entangled. So we don't need necessarily to go to a 2D implementation. But also, as you said, ions can be shuttled around. So if instead we had like little bridges in here, you could shuttle ions around and get a 2D connectivity, something like this. Great question.
So you showed that essentially single ion, we can create one superimposed state using a single ion.
Yes.
And then you showed the multiple ion business.
Yeah.
Is the idea that you're looking at multiple ions just for individually addressable channels, or creating superimposed states across multiple ions? That's one question. And the second thing, to get away from that huge lab and lasers that you showed, is the solution really integrated photonics? Is that the path forward?
Yeah. So first question, we want, so to the multiple ions, you'd create some sort of entanglement or like large state within the larger space mapped out by all those two ions, the two states. Right, so in the end, you'd have these lots of ions, you'd entangle them, you'd create some large state that hopefully, as you're doing gates upon it, in the end, measuring all of the qubits will give you some encoding of the answer that you want. So yeah, you need all of those to do anything useful. It's a really good question about integrated photonics. I think that actually some of the answer to move away from something that looks like this is just better engineering of laser systems. Not everything has to be integrated. Maybe someday it will, but you can get a lot better. And actually, if you come to the lab now, we have almost all of the technology that's in this picture, but in a single rack, right? And that's not a thing that we did. That's just companies have gotten better at making systems more compact and more plug and play. But I think a final solution will always have integrated photonics. It remains how much of it will be integrated photonics. Yeah.
Last question. So the integrated photonics, so what do you think result? Like, is it like multiple, like some heterogeneous integration? Or
You mean in a final, like something like this?
Yeah, or is it like an integrated photonic chip is still interfacing on a space?
Yeah, it's a good question. So it still remains to be seen. I have so people have shown a single chip with different layers, one of which is electrode layer, which is a waveguide layer. That has pluses and minuses. I think in the near term, there's no need to have, there can be some free space optics. Yeah, I think there's no obvious answer. Yeah, we have some ideas.
Okay, really last.
One key area of research in like PICs is 3D manufacturing and 3D design. How would that actually affect some of the architectural constraints? For example, would it be possible to implement a planar or an array of qubits, or even like a three-dimensional structure? And would that have any advantage towards realizing specific quantum problems?
Yeah, I think that what a 3D architecture, so 2D architecture we can make. 3D architecture we have not, it has not yet been shown with ions, and it might help. I would say with our current technology, it'll just make things more complicated, but it might be the answer to being able to, if we think about how much space you need in a plane to trap 1 million ions, maybe that starts to look like meters. And so maybe doing some 3D integration will help make everything a bit more compact. So that's a good question.
Okay, let's thank Sara again.